This is the data sheet for the Intersil large-scale integrated chip. It is an ICM 7216, and the version we have is the D version, which when you read this, turns out the D version is identical to the B version with one difference, the difference being that the D version lets the device control where the decimal point is located, whereas the B version handles everything from soup to nuts. So you can see that the chip itself is capable of acting as an independent frequency counter all the way up to 10 megahertz, frequencies to 10 megahertz. The chip supports gate times as low as 1/100th of a second, but this device only uses 1/10 of a second, 1 second, or 10-second gate frequencies. It also does all the LED driving. It can work on a single 5-volt power supply, which is actually logical for a battery-powered device. The 4 NiCads were in series, the 4 NiCad batteries. Each developed 1.25 volts when fully charged, so you get your 5 volts there. It also drives the crystal oscillator. In this particular application, they're using a 10 megahertz crystal. The idea of these large-scale integrations was to reduce the component count and the chip count. In those days, perhaps even today, in those days, chip count is what really drove the fabrication costs of a circuit board or a product. It wasn't so much what was in the chip, whether it was an expensive chip or a cheap chip. It was how many chips you had, how many components you had that had to be soldered, particularly when we're dealing with through-hole circuit board technology compared to today's surface mount technology, which is all robotized. But there, everything had to do with labor in the 1960s, 70s, 80s, and early 90s, when through-hole was still being used. It was all labor-intensive. And that's where your money went. So the price of the chip was secondary compared to the number of devices that you had to put onto the circuit board. And every device that you had to put onto the circuit board also represented another point of failure. So the fact that they could bundle all these features into a single integrated circuit made the chip somewhat more expensive, but it reduced the parts count significantly, and that was what made these chips so economically desirable. So let's continue down, and you see here that the D version, that the decimal point is up to the device. The device can control the decimal point, and in this case they're also saying that leading zeros are up to the device to control. It is a standard 28-pin DIP package, what they called PDIP at the time. Anything else we need to know? And you can see here that they have all these components built in. This is the block diagram, and so they're controlling the oscillator there. This is all the LED driving logic circuit here. These are the counters right here that are accumulating the pulses between gates. Boom, boom, boom. So if we had a 1 second gate, it's going to count up all the pulses that arrive over the 1 second. When the crystal oscillator counts to 10 million, that means a second has passed, and whatever count has accumulated in the timer, that is sent to the display logic and shot out the LEDs. What they are saying here is that it'll go all the way up to 6.5 volts. We don't have to worry about that with the internal circuitry being nominally 5 volts. It is... This is not how much the chip consumes. These currents here are how much they can drive the LEDs. Back in the 1970s and 1980s, light-emitting diodes were not that bright for a given current. today you see insanely bright 7-segment LEDs, which work on very little current whatsoever. It wasn't that way in the past, so you could drive the LEDs almost to 400 milliamps. Now keep in mind that's strobing them, meaning that it's not a continuous 400 milliamps. It would be 400 milliamp burst, and then the driver circuit would move on to the next digit. Anything else we need to see here? No, nothing else we need to see here. So now let's look at the other chips and see if we can figure out what's going on with them. So there is the 74196, which I explained to you before, which is a transistor TTL, transistor logic integrated circuit. This is the package that we have. We have a 14-pin DIP. It came in other packages, but those were more for military use. This here, your ordinary Caterpillar DIP. And what this is, it's a decade counter. It's usually configured to be a divide by 10. However, the circuitry is exposed to allow you to do a divide by 2, a divide by 5, or a divide by 10. So it has the gates here, and it looks to me as if the frequency counter is using this chip as either a divide by 5, a divide by 2, or a divide by 10 to scale down the high megahertz frequency that are coming in the BNC inputs to get them down below the 10 megahertz limit of the intersil package. Remember, the intersil, let's go back to the intersil. Where is it? We lost it. We lost it. We lost it. We lost it. Where is it? Where is it? Where is it? Where is it? Okay, the intersil package. Right. The intersil package can handle input frequencies up to 10 megahertz. So if you're building a device that's going to go up to 600 megahertz like this one, you've got to cut down those frequencies to a range that this intersil chip can handle. So that 74196 is being used. Where is it? Where did we just have it? Oh gosh, I'm losing everything here. The 74196 is being used in a way that it reduces the 600 megahertz or the 60 megahertz down to a speed that the intersil chip can digest. And quite frankly, I'm going to speculate that it's probably doing a divide by 10 such that the digits from the intersil chip are uncorrected, and by dividing by 10, all you have to do in the logic of the circuit board is simply move the decimal point over one digit to correct for your divide by 10. So in other words, if I have a 100 megahertz signal coming in and I divide that internally by 10 before I feed the intersil is going to present 10 megahertz on the digits, but it's not going to put the decimal point in there because we have the D version. We're going to move the decimal point from after the 10 to after 100. We're going to shift the decimal point over to the right by 1 so that it displays 100 because we know we cut down by a factor of 10. So we have to, on the display, we have to shift that decimal point over to boost the number by a factor of 10 so that the user is seeing the frequency that's coming in the device, not the frequency that's being fed into the intersil chip. Okay, so we know what the 74196 is doing. Now let's have a look at this thing called the 10116 line receiver. Okay, this is not doing any division. And again, we have a DIP version. All this is doing is signal conditioning. So what's happening is that the machine cannot control the quality of the pulses that you're sending in. They could be sine wave, they could be triangle, they could be arbitrary waveforms. And the intersil chip is looking for clean square wave input. So this chip here is going to be part of the circuitry that'll be used for conditioning the rough edges of the input signal and cleaning them up so that we spit out a nice clean square wave as an input to that intersil comprehensive chip. We have one more chip to look at. Let's see what it is. It is... no, that's not what we want. We want... Where is it? Where is it? Where is it? Here it is, the 11C90. This is a 650 megahertz prescaler. Okay, this is another divide by 10. Yeah, now this is a device that is capable of running at 650 megahertz. So this is going to be on the 50 ohm input, because it's the 50 ohm input that can accept frequencies up to 600 megahertz. So this device here was chosen to be a prescaler. Yeah, it'll divide either by 10 or 11. I'm guessing it's going to be a divide by 10 to cut the 600 megahertz down to 60 megahertz, and then that other 74196 chip will cut it down by another factor of 10. That'll bring it down to 6 megahertz before it goes into the intersil, but we'll just play with the decimal points. So this thing here has the capability of going up to 650 megahertz. So the OptoElectronics people are not using the full capability of this chip. They're only allowing signals up to 600. All right, so we know what our chips are now. Let's go probing around to see whether or not these chips are getting the proper voltages.